Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, a few things as usual before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, and you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you. Many other people around you have faith in you, so should you. Number two, please feel free to follow me here on YouTube, on Twitter, or on LinkedIn. That way when I upload a new video, you know about it. And on the topic of the video, if you like it, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist, because that does encourage me to keep making them. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video on YouTube, and I will try to take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over very basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to understand what's going on, but also why. So all that being said, let's go ahead and get started. So this video is the next in our series on inferential statistics. And it's actually sort of part 2 of the previous video. In that video, we looked at the concept of confidence intervals. And more specifically, we looked at confidence intervals when we knew the population standard deviation. So in this video, we're going to talk about confidence intervals when we do not know the population standard deviation. That's why you can see here in parentheses, it says sigma unknown. And this is actually the most common situation. So when we're trying to estimate a population parameter, we do not have the population standard deviation to work with. Therefore, we have to estimate it. So this is sort of the second flavor of confidence intervals. So, all that being said, let's go ahead and dive right in. Now, just a few reminders. Like I said, in the previous video, we covered a lot of the basics. So I'm not going to go into depth about those things in this video because it'll be redundant, but I will sort of hit the highlights as we proceed. Just remember that in the preceding examples in the other video, we used the terms confident and interval in the form of like a plus or minus. Now, when estimating a population parameter using a sample statistic, it's never going to be perfect. There will always be some error built in, and that is fundamental to the idea of estimating a parameter about a population. The population, like I said before, may be 1 million people, but there's no way we can go out and collect survey data or whatever else it might be on all 1 million people. That's just not feasible, it's too costly, takes too much time, etc. So we take a sample. But our sample estimate is never going to be perfectly representative of the entire population. So we're always dealing with this idea of error. Now we can express that error or uncertainty using an interval estimate, and it follows this general form. So we have some point estimate, like we're going to estimate the population mean, plus or minus some margin of error. And I'm sure you've seen this on presidential polls. So it'll say 58% of voters think this, plus or minus 3%. Well, that's the margin of error. It's a proportion margin of error, but the same idea. So you've seen this already in your everyday life. So we're just going to talk about it more specifically in the statistical sense in this video. So what about confidence intervals and standard error? Now, in the previous videos, we discussed the standard error of the mean in great detail. So recall that to find the standard error of the mean, we need to know two things: the population standard deviation, and 2, the sample size. So we have to know those two things. Now, most often, as in this video, we do not know the population standard deviation, and therefore we have to estimate it. Now, also remember that for any population standard deviation or its estimate, increasing the sample size up to a point reduces standard error. So this makes sense statistically, but I actually want you to think about it more in sort of in common sense terms. if we take a larger sample of our population up to a point, it's going to be more representative, or it's more likely to be representative of that overall population. So if my population is 1 million people, I'm not going to go out and survey 4 people. That's not going to be very representative of the population if we only survey 4 people out of the 1 million. So we're left with the idea that the confidence interval will be affected by all of these points, all of these concepts. The standard deviation of the population, the sample size we are taking, and the level of confidence we are satisfied with. And that's sort of the plus or minus, okay? So I always want you to keep these 3 things in your mind: the overall standard deviation of the population, the sample size we're working with, and the level of confidence we are satisfied with for the mean we are estimating. Now, a quick reminder, just remember that when we're dealing with curves, that the area under the curve is 1. That's the same thing as saying the probability under the curve is 1. So everything to the left of the midpoint would be 50%. Everything to the right of the midpoint would be the other 50%. And of course, we can chop up this area in many different ways. So in these type of videos, we're interested primarily in the middle 95%. And we'll talk about that here in a second. So in this video, we're dealing with a special type of distribution. And I'm sure you've probably heard of this in your stats class or somewhere else, but it's called the student's t-distribution. So what makes the student's t-distribution different than the standard normal distribution? Well, the shape is not all that different. And actually, I just went ahead and used the shape of the normal curve because we're really talking about small variations for the most part. So it will look, the distribution looks like a normal curve. It just has a little bit different dimensions, which I'll talk about here in a second. The area under the curve is still 1. The probability under the curve is still 1. Now, in these situations, when we're doing the confidence intervals, when we do not know the population standard deviation, we have to estimate it. Now, this estimation, this uncertainty, forces us to use the student's t-distribution instead of the normal distribution. Now, just a few reminders in case you're reviewing this, or if this is new to you, I just want to point out some of the characteristics of the student's t-distribution versus the standard normal distribution. So, number 1, in general, the t-distribution is shorter in the middle, so it's height in the middle, and a bit fatter in the tails. So, again, we'll talk about this in a second, but in general, shorter in the middle and a little fatter in the tails of the distribution. There's more probability in the tails, and there's a little bit less near the mean there in the middle. And this is sort of saying that because of that increased uncertainty, there's a greater chance of having extreme values further away from the mean. Now, number 3, there is not just one t-distribution. So in the standard normal curve, there's just one of them. It's the standard normal curve. But for a student's t-distribution, there is a t-distribution for every sample size. And the t-distribution is referred to as the t-distribution for some degrees of freedom. And in this case, the degrees of freedom is our sample size n minus 1. So, if our sample was 30 in size, our degrees of freedom for the student's t-distribution would be 29. And we'll talk about that again here in a second. Now, the smaller the sample size, the shorter and fatter the distribution, the more tail probability there will be. So as the sample size gets smaller, we're going to have a higher probability of more extreme values away from the mean. However, as the sample size becomes large, the t-distribution converges towards the z-distribution. So usually once you pass a sample size of around 100, the z-distribution and the student's t-distribution are basically indistinguishable. So again, we'll show a little chart here in a couple slides about how that works. So just remember, when we do not know the standard deviation of the population, we have to use the student's t-distribution instead of the normal distribution. Now, the distribution we're actually talking about here is the sampling distribution. So this curve is not representing the population. It's actually a distribution of sample means. So if we took many samples and another sample, another sample, another sample, and then we took all those sample means and put them in their own distribution, this is what we're looking at. It's a distribution of sample means. Now the distribution has many sample means in it, and they're all of the same sample size. So all these sample means in this distribution are from samples of the same size. So as I said, we can divide up this probability distribution into sections. And in many cases, and the majority of cases I would say, we use the 95% probability interval of the distribution to do these type of problems. So what we're looking at here in the light blue is the middle 95% of the overall probability of 1 that's under the curve. So what we're saying is that 95% of all sample means are in this blue region. Now therefore we have 5% left evenly divided between both tails. So that's the green region there. The area in the tails is called alpha. So in this case, alpha is 5% because the blue area is 95%. Everything has to add up to 1. Therefore, the green in both tails is 5%. Or as a decimal, it's 0.05. Now that's evenly divided between both tails because this is symmetrical. So if you've ever seen in a formula somewhere, you have alpha divided by 2, that's where it comes from. We're just taking the leftover probability in the tails and dividing it evenly among both sides. So in this case, we have 5% divided by 2, so we have 2.5% over here in the left tail, and we have 2.5% over there in the right tail. So that's 0.025. So in formulas, you'll see Z A over 2, or maybe T A over 2, alpha over 2. And that is really what we're talking about, is the boundary, upper and lower, of this 95% probability region. And that will change depending on the problem. But what we're talking about when we see in a formula Z alpha divided by 2 or T alpha divided by 2, we're actually talking about the little black lines down here in the distribution. So I want you to visualize that in your mind as we go forward and see that in formulas. So what's actually going on here? Now, in this state of the slide, I have labeled the boundaries of the 95% region using a standard normal curve. Now, in the previous video, we talked about these boundaries for certain percentages that we use commonly. 95% is the most common. And what that comes out to in the standard normal distribution is a z of negative 1.96, so 1.96 deviations below, and a z of positive 1.96, that's 1.96 deviations above. So to capture the 95% probability in the middle, that creates boundaries at negative 1.96 and 1.96. Now, if we do not know the population standard deviation, we treat this distribution as a t-distribution. So that brings in a whole new set of issues. So by doing so, we can assign t-scores to the upper and lower boundary of the 95% interval for each sample size. So as we're looking at this probability distribution now, we're using the standard normal distribution. It's always going to be 1.96. When we go over to using a student's t-distribution, those black lines are going to shift depending on sample size. So there are many different spots along there, and we'll talk about that here in a second. Now we use the concept of degrees of freedom to know where those boundaries are going to be when we're using the t-distribution. So let's take the case of a sample size of 10. So n equals 10. Therefore, the degrees of freedom is 9. That's n minus 1, so 10 minus 1 equals 9. Now the question is, where are these boundaries going to be for a degrees of freedom of 9 in the t-distribution? So in general, what's going to happen? Now compared to the standard normal distribution, the curve is going to get slightly smaller in the middle. It's going to get a little bit wider on the ends because we have more probability out there. And we'll have new boundaries there where the red dotted line is. Now I know that this is a t of negative 2.26 on the left and positive 2.26 on the right. So the metaphor I use is a very crude one, but when we're using the student's t-distribution, think of a sandwich that has maybe too much ketchup or mustard or something on it, depending on where you are in the world, maybe something different, and you bite down on it. What happens to the excess stuff? Well, sometimes it comes out the sides. Well, that's like this curve. So when we're using the student's t, we kind of bite down in the middle, and then the extra squishes out on the ends, and therefore the boundary moves. So in this case, it's negative 2.26 and positive 2.26. Now the question is, how do we come up with those numbers? We come up with them by using a t-distribution table. And if you have a stats book, it's in there, probably in the front cover or in the appendix somewhere. Of course, you can find them online virtually everywhere. So let's take our standard curve here, or a curve we're using. This is going to be a t-distribution. So we have our middle 95% or 0.95. In each of the tails, we have 2.5% or 0.025. Now we know that this is a t of alpha over 2 for degrees of freedom equals 9. So what is alpha over 2 in this graphic? Well, alpha divided by 2 is 0.025 because our alpha was 5% divided by 2 is 0.025. So the alpha divided by 2 is just the probability in one of the tails. So now we can go to our t-distribution table. And again, this is in every stats book you've ever laid your hands on. Of course, you can find them online. So remember, we're interested in finding the t-values of the boundaries, the little black lines, in our distribution. So what do we do first? Well, the first thing we do is we find the column where it says 0.025 for one tail or 0.05 for two tails. So the 0.05 is the sum of the probability, and of course the 0.025 is the probability in each tail separately, but they add up to 0.05. So that's the column we want. Now, over on the side, what row do we want? Well, you can see we have degrees of freedom, and we're interested in 9 degrees of freedom. So basically, we find where that column and that row intersect, and it happens to be right there at 2.262. So what that's telling us is that the t-values of those lines sort of at the boundary are 2.26. So 2.6 above and 2.26 below. And that's how we use the t-distribution table to find the probability boundaries in our distribution. So let's do some comparisons here of the 95% distribution. Now remember, in the standard normal curve, or the z distribution, the 95% boundaries are at plus or minus 1.96 standard deviations. Now what about the student's t-distribution? So let's look at the pattern here. If our sample size is 10, we have 9 degrees of freedom. So the interval, or the boundary, is plus or minus 2.262. So let's go up to a sample size of 30. That's degrees of freedom 29. Now the interval is plus or minus 2.045. So what happened to the interval? Well, it got narrower. Why? Our sample size increased. Let's go to a sample size of 75. Degrees of freedom 74. Now our interval is plus or minus 1.993. And again, we just pull these from the t-distribution table we had before. So what happened to the interval again? Well, it narrowed even further. Why? Our sample size went up. Now look at the sample size of 100. Degrees of freedom 99. Now our interval was plus or minus 1.984. So the interval decreased again. It's decreasing by smaller amounts, and it's important to sort of point that out. But it is decreasing as the sample size goes up because our standard error it's going down. But what's happening here is that as the distribution narrows with a greater sample size, the t-distribution narrows with a greater sample size, it will converge on the standard normal curve. And that's sort of what I said before, is that as the sample size gets up around 100, the t-distribution and the normal distribution are, for all practical purposes, the same. So, sample standard deviation. When we do not know the population standard deviation, we use the sample standard deviation to approximate it. So we take a sample, maybe of 50 people or 50 items, whatever it might be, and then we find the standard deviation of that sample, and we use that to approximate the population standard deviation we do not know. This approximation comes at a cost, though, in terms of our interval estimate, as we've seen with the t-distributions. So we must use the t-distribution and not the z-distribution to account for this estimation of sigma, the population standard deviation. Now, every sample size will have its own t-distribution with degrees of freedom of n minus 1. So our standard error will now be s divided by the square root of the sample size. Now remember, in the other type, when we know the population standard deviation, it's sigma divided by the square root of the sample size. So S in this formula stands for the standard deviation of the sample, because we don't have the standard deviation of the population. So different standard errors. In the previous video, we knew the population standard deviation, sigma, and it was therefore fixed in the standard error formula. So that was sigma divided by the square root of n. And no matter what sample size n we took, that sigma never changed because it was sort of a given. This meant that all samples of the same size had the same standard error, because the top of the fraction was fixed, and then we had the square rooted sample size in the denominator. So a sample of that same size would always have the same standard error. Now, when sigma is unknown, we estimate it with the sample standard deviation S. Now, since every sample will have a unique standard deviation, samples of the same size do not necessarily have the same standard error. So, when we're taking samples, when we're using their standard deviation to approximate the population, samples of the same size do not necessarily have the same standard error as they would if we knew the population standard deviation. Now, the randomness of sample selection is represented in its standard deviation and therefore its standard error. So every sample will be unique. It will have its own mean, its own standard deviation. So it's kind of like a fingerprint that will have its own characteristics, and therefore it will have its own standard error as well. So, quiz. What is the standard deviation of the sampling distribution? Well, the standard error of the mean. Remember, the standard error is just the standard deviation of the sampling distribution. And the standard error is largely dependent on what? Sample size, because at the bottom of the fraction is the square root of the sample size. Now, if sample size is small, what will happen to the standard error and therefore the distribution? Well, the standard error will go up and the distribution will become wider, because the wideness or the width represents the size of the errors. So a larger standard error means a wider distribution. And you can see that by looking at the formula. If the sample size is very small, that's going to increase the value of this fraction. So how do we interpret this? And this is the hard part for many students to wrap their head around, because we don't interpret these in an intuitive way, unfortunately. Point number one, remember that the randomness lies in the elements chosen for the sample, not the population mean. So the population mean is a real number of the population. It's fixed. It's there. The randomness lies in the elements chosen for the sample. It's the probability of obtaining a representative sample. And again, that's related to sample size, right? So the larger the sample size, The bigger net you're casting over your population, and since you take a larger sample size, you are more likely to capture all the diversity, all the different characteristics of the population if that sample is larger. You can also think of it as the proportion of samples for any given size for which our estimate, the sample mean, is within a certain distance of the true population mean. The sample mean is either within that interval or it's not. There is no gray area. It's either in or it's out. You can also think of it as the probability that the sample mean of size n is within a certain distance of the true population mean. So proportion, probability of that mean being within that distance. Now here's the common error that many students make. The confidence interval is not the probability that the population mean lies within the interval. Let me say that again. The confidence interval is not the probability that the population mean lies within the interval. It's actually the opposite. It's the probability that the sample mean lies within that interval. And that's that's the difference. Because when we say the probability of the population mean, we seem to be implying there is some randomness in the population mean. That's not the case. The randomness lies in the sample. So it's not the probability the population mean lies within the interval. It's the probability the sample mean lies within that interval. So if you ever write there is 95% probability the population mean is within the interval of blah, 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 wrong answer. Okay? So we're not talking about the population means probability being anywhere. We're actually talking about the sample means probability of being in that interval.